Okay, I haven't looked online. How'd it go? Everybody got their things turned in? All right. Now, actually, let's look at schedule real quick. I think. Okay, so we put this in on Monday, and then as to the description, your hypothesis, background section will be, I've got it for this Friday, but I think that doesn't make sense. So here's the good news about it. I think we should push it to give you time over the weekend because the background is not trivial to fill out. But if we do that, then the experiment design and simulation design will be a little bit compressed. So just be aware that you're going to want to pull this together pretty quickly. The experiment design is not going to be, I don't think they'll be that difficult. If you laid out your background, described, made a description about what you want to achieve and not achieve with your model or with your simulation, and then identified some variables, you've identified your research questions, then your experiment design kind of falls out from that. The model design can be a little more difficult. Now, you guys, the whole thing is the model design, so you're in good shape compared to some other people, right? Your model design, what do corridors look like, right? How are you going to model the behaviors? What behaviors are you going to include, not include? What physics are you going to include, not include? Probably very little physics, right? Preston, you have a lot of physics, right? You're all about physics, and as you said, the first thing was even getting stability of the vehicle. So that's going to be a little bit more tough. So be aware. I'll set this. I'll set this up so that the next deliverable gives you some time over the weekend, with the understanding that the next deliverable will be a little tight. I'll still probably move it from Friday to Monday to even the following weekend, but still. Okay. Questions about that? All right. I am, make sure I'm recording. Yeah, I'm recording. Okay. I'll have this in yesterday's lecture. That should be posted to YouTube tonight. Okay, so we've talked about the last couple notes here that we talked about yesterday, giving some basic definitions about agent-based simulations or agent-based systems. And so here are some more definitions about how you can categorize agents. So basically, you can categorize them with respect to the degree of information they have available to them, the amount of planning that they do, the amount of communication that they do. So a reactive agent, this is about how, quote, smart they are, or how much planning they do, okay? A reactive agent is literally you got poked with a needle and you jump back and say, ouch, right? You are reacting to the situation. So the reactive agents, every time you go through a time step or an event in your simulation, they're taking in their immediate surrounding, they're observing their immediate surrounding, and then they are making a decision at that moment based on that situation with no regard to the future, no regard to the past. Purely reactive. I'm putting the term in here about AI, and these notes were written long before these large language models came about, but the existence of the large language models doesn't change the underlying theme here. People are overusing the term AI. Again, an agent, as we said before, is a decision maker. And if you told somebody who was not in modeling and simulation or not in computer science or systems engineering that an agent is a decision maker, they would instantaneously have a mental picture of a wise decision maker, right? Because that's what that term generally means. They're going to lay meaning onto that term that is not there. And then if you say, oh, that means like a dice roll is a decision maker, right? That's an agent. So that's pretty stupid. Okay, so everybody though still will use the blanket term artificially intelligent for these things, regardless of their actual level of knowledge, deliberation, planning, capabilities, any of that stuff. Now, having said that, large language models have come a long way towards providing a good illusion that they are being deliberative. And in a sense, they are, because they're looking at, they're gobbling up all kinds of past data in order to try to make a decision in the present about how to respond to your prompt. But in the end, they are still in many ways dumb agents. So just be aware. The reason that we start to develop these terms is so that we can get away from that blanket AI term or the blanket agent term and start to say, look, I have an agent and here's how I'm going to describe it. It's dot, 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 dot. And just using a few words at a time, you can provide a lot of information. That's why all disciplines have jargon, right? So that you can supply a lot of information in a very efficient way using the jargon. So, reactive agent. The decision making is moment by moment, as opposed to a deliberative agent. So, a deliberative agent is some kind of a planning agent. You're making decisions generally in conjunction to past or future. So, if you one of the earliest agents that people had experience with are chess playing computers and checker playing computers. The first checker playing computer that was an AI agent, meaning that it learned from playing games of checkers, I believe was 1958 or something like that. It was quite a while ago. When I was a young lad in the mid-70s, they were coming out with chess players that were good enough to market. And so I had a chessboard that was electronic and you could set the level of hardness and the machine would play you a game of chess and did a fairly good job. Nowadays, chess computers, chess agents have basically bested all the human world-class chess grandmasters. The game of Go had not been conquered by computers until just really recently. I'd say within the last 5 years or so, the computers are starting to beat human Go grandmasters. So let's go back to chess for a second. In the 70s, how do you think the computer was actually capable of playing a game of chess? What do you think the algorithm for the computer was?
It knew every single board option was.
It would brute force attempt every single move and then every single counter move. Now, when I say that, I don't mean every single reasonable move or every single smart move. I mean literally every possible, I'm as dumb as this computer, this move is possible, so I'll see what happens. So it would play ahead one move that it makes and then your response. Every single move. And then it would score it. And that's kind of where the quality of these things would come into play, is how well it could score a good move versus a bad move. And how do you make the computer, quote, smarter? You add in more moves. So it's going to look at every possible move that it can make, every possible response that you could make, whether it's relevant or not. This is true brute force. And then every possible move it could make in response to your move and every possible move you could make. So now it's looking 2 moves ahead. And how do you make it smarter? You make it look 3 moves ahead. Well, the problem is if you do combinatorics, which is the study of counting things, the number of potential moves, 3, 4, 5 moves ahead, is what we call combinatorial explosion. It's a huge number of moves. And the chips of the day were slow enough that they couldn't, in a good time frame, look very many moves ahead and brute force their way out of the situation. But that's a way to plan, right? That's a planning agent. Now, how are they doing it now? Oh, they're much smarter. You know, one of the things that humans are good at is we're able to take, instead of all possible chess moves, we're able to what we call prune the tree, right? We prune the decision tree and we only look at reasonable moves, hopefully reasonable moves. So we're able to get rid of a lot of clutter and not waste our time investigating ridiculous, stupid moves. What I found back then was if I was playing a human opponent and the human opponent made a move I didn't expect, sometimes it was a really good move, sometimes it wasn't. With the computer, if it made a move I didn't expect, it was always a better move. It was always a good move. And the reason is it's literally trying all possible ones and picking what it thinks is the best one based on the scoring algorithm. Nowadays, the computers are pretty good at pruning. They're invested a lot in pattern matching, neural nets, things like that, right? So over time, because this thing is played, you simulated billions of games and then fed the results of that into the model that the computer's using, it can pick up on different patterns. And so it's able to do some pruning on its own. But even that was a huge computational task. Yeah.
Didn't that lead though, for a while there where the masters would make an unexpected, a suboptimal move and would throw the AI off completely?
And that's where AI is what we call brittle, right? So a robust system will respond well to unexpected events, and a brittle system won't. So then, right, you can play games where, and I'm not aware of this historically, I'm trusting of what you're saying, but if someone makes if the computer's model is based on the assumption that everybody will always make the best move, and then you end up making not the best move, what you've done is broken the model. And if the model's brittle, it won't respond well to you, right? Whereas with a human, if you make a suboptimal move, they'll increase their strength over you, right? They'll increase their position in the game. And we're going to rule out just dumb stuff, like sacrificing a queen for no reason. The computer would pick up on that suboptimal move, right? It has to be something fairly subtle. I would suspect that that's been passed over. Yeah. And you hear, and again, these are things that it's good to be aware of when you're dealing with software agents. We tend to anthropomorphize everything. We are literally hardwired to anthropomorphize everything. So we're always going to put human attributes on things. And so with the computer, we make the assumption that they're going to behave and respond like a human. And that's not a good assumption. And there's an example right there. With a human, if you make a suboptimal move, they're so happy because they just got into a better position in the game. Whereas with a computer, in that situation, you just broke the algorithm. It didn't know how to respond. Okay, so we have all kinds of deliberative agents. And again, some will keep a record of the past and some won't. You can imagine if you had a simple maze and then you have an agent trying to traverse the maze. And quite frankly, people study this a fair amount. But the agent didn't keep track of its past history, then it would be easy for that agent to very inefficiently explore the maze by going down the same dead end over and over and over again, because it didn't keep track of that dead end as a dead end. So that would be an instance where I'm giving you an example of where, say, a reactive agent and a deliberative agent would differ. It would be normal, right? If you were constructing an agent to traverse mazes, it would be normal for you to immediately start to say, oh, maybe this thing should keep track of where it's been. In other words, you're going to make probably a default decision to say deliberative agent, whether you're aware that it's a deliberative agent or not. In the long run, or in a more extreme version of a deliberative agent, if we truly use machine learning, then what we'll do is you develop a machine learning system that's completely different project than developing an agent-based simulation. And then within that learning system, you just run that agent through simulated event after event after event after event. And as you know, there's whole other classes you can take just on artificial intelligence and how to create machine learning systems. But then what happens is that you come up with a deliberative agent, but it's deliberative based on having a set of rules or some kind of a structure in place that helps guide the decision making in the moment based on perhaps hundreds of thousands of trials offline. And there's generally, with those kinds of agents, where you have learning agents, they learn offline and then you put them in the actual operational environment or the real quote simulation, and then that you freeze their learning at that point in time. Now you can have agents that learn during the simulation, true learning. True learning. Learning means changing your behavior, by the way. It's a very neutral term. I mentioned, by the way, that in some places in the world, and there are elevators in buildings, and the elevators are learning agents, meaning they're learning in place in that building what the daily pattern is, and then trying to optimize their positioning, right? If there's no people in me, where should I hang out? And that may change based on the time of day, but that would be an example of deliberative agents. Okay, adaptive agents, they change their behavior over time. So we could use the term learning agent. We could use the term, you can use the term artificially intelligent, but notice that again, there's a distinction there. The distinction is something can be artificially intelligent, but not adaptive, meaning or artificially intelligent, meaning you've given it some kind of a rule set for it to perform its behaviors with, but it's frozen. It won't change, as opposed to a learning agent. In the history of video games, it's been interesting to watch the computer-generated agents change over time. In the early days, if you walked into a room and there was a computer-generated character in the game, that character, if it was supposed to interact with you in any way, would do whatever its interaction was. Usually it tried to shoot you, right? It tried to kill you. And then you leave the room and you go back in and it's there again and it acts like it's never met you and it performs the exact same behavior again. This is back in the 90s, okay? Then they got a little smarter where if you went into the room, they would react to you. And if you left the room and came back in, they would react to you as if you had met before, as if you were still continuing that interaction. And then they got a little smarter where if you entered the room, they would react to you based on your behavior. So if you ignored them, maybe they would ignore you. But if you tried to do something to them, they would try to do something to you, and this kind of thing. And now it gets into kind of a choose your own adventure style, right? Oh, you see the lab technician. What do you want to do? Kill him? Talk to him? Rob him from his lab coat? Whatever. So you started to get more of these things. Now, I don't play video games, so I don't know what the current state is, other than they're pretty darn sophisticated. And what I'm wondering is, I don't think they are adaptive agents in the sense that they learn and change over time, but they certainly could be. So I don't know if there's any games out there that have non-player characters that are learning over time based on the thousands of interactions they have with people online.
So first there's the game, I think it was Dark Souls, came out 10 years ago. They're still under patent for it. But basically they have the nemesis AI. It would randomly choose one of the AI to become your nemesis. And basically every time you killed it, it came back with a counter to whatever you're.
Okay, almost Borg-like, right? It kind of,
Well, it'll come back later.
yeah, okay.
In the game. And essentially the idea was that it just got more and more powerful. And it would learn from the way that you react.
Uniquely with your, like your account for every time you logged in. So it would be unique to your,
Single player.
to it, yeah.
You now have the game and Star Citizen, and I play that pretty exclusively. They have their regular VCs that are that just do their daily tasks and everything. Then they have their agents. They are literally called agents or Quanta, depends on which developer is talking about it. And some of them, which especially the aces, will actually learn your tactics and learn from the flight data of all the players involved, and they become not quite your quote nemesis, because that other saw that is under patent still,
Right.
but they will become stronger against any player they encounter.
But you can imagine, well, I have to come back to the thought. You can imagine, yeah, how from a game design standpoint, that's a tough decision. So for example, if you have a computer generated agent that is some kind of a opponent in the game, and there's 100,000 people online all the time, that thing is gaining so much experience in developing its patterns, right? Now again, because no matter who's playing against it, it can always port the encounter to a common area and use that as a training exercise.
It's whenever it fights somebody, the problem is.
That's true. You have to have some kind of a filter on it, which they're very poor at. But you can imagine that you're online, you're one person, and you have so many encounters a day in order to get better. But if this thing's having 100,000 encounters a day, is it getting better? Now, from a game design standpoint, you do not want to create a undefeatable opponent, right? That's not a good game. That's the goal of Nemesis, is to eventually make it where you can't win.
The ace is eventually. I mean, right now, unless you're like one of the top PvP, or unless you're one of the top PvP pilots, it takes 2 to 4 people to take them out.
By the way, does anyone else play? I don't play at all. You play? Anybody else?
And tell me to shut up. I have no problem being.
What's your experience with these things? Are you noticing that are you noticing that any of these characteristics in these things?
It's gone from just like simple dialogue to like preset, like that's what you say, to like where they like learn from you.
So one of the things large language models do well is create dialogue. So it wouldn't shock me if instead of having scripted dialogue, they're moving to this more interactive mode, because from the standpoint of holding a grammatically correct conversation, and almost always a realistic conversation, large language models have basically passed the Turing test, so they could do that. However, I wouldn't think still, other than these special purpose games, the characters are learning over time and truly adapting their behavior. Do they remember their history with you? Have you ever played Grand Theft Auto? That's been the big sandbox game for a long time. I've never played.
So Grand Theft Auto's MDC model is about 2 or 3 generations old. That's why everybody's excited about GTA 6.
But even then, did it remember your history? Like if you met someone and then later on, 10 days later in game time, you met them again, did they remember?
No, because the problem was most of the missions was basically kill all people.
Okay.
So, and they were, and those were kind of instance missions, basically the instant reaction you in isolation to the reaction.
Okay.
So you could be having this massive gunfight, somebody could be walking right by and never even see you. And then there can be the one where it's happening in the open world too. So it's
All right.
not quite the same. Your crime stats about the only thing that really happened.
Notice the comment there too about adaptive versus learning. Learning has again, as a human, when we say learning, we mean that the behavior improved, right? When you say, "Oh, I learned something," that means you have a skill that you didn't have before, as opposed to adaptive, which is just a more neutral term. It's a change. And in the context of an agent, learning literally just means it changed its behavior, so it's adaptive. So you can have negative learning. It's more easy to have negative learning. I don't know if that's true. You can have negative learning in a computerized environment, with a software agent, as opposed to generally with humans. Once you have a skill, you don't lose that skill. Generally.
So,
Other than disuse.
interesting thing, I've been watching a guy develop an AI that runs race. And at first, it didn't know how to do a drift. And essentially, what it eventually figured out is that instead of trying to drift around corners like all those players would, it would just slam into the wall and go full. What's that one dude NASCAR? You just ball roll the entire corner at max velocity.
And
it would just do that for certain corners instead of trying to drift like a normal player. And essentially lost the ability to drift, and we had to retrain it.
There's a subset of machine learning that you're reminding me of, which is if you want to have machine learning of a behavior, and let's say that behavior is composed of some smaller behaviors, so you train up for each of the smaller behaviors, and then when you try to train up for the larger behavior, how can you be sure that you didn't lose one of the smaller behaviors, or that in the process of combining these things, you don't regress in one of the areas? There's issues with that kind of thing. Again, the large language models that are coming out are really impressive. However, we always must be aware of their limitations. They really don't have a way to do filtering and self-checking and self-awareness yet that we tend to use to maintain the quality of what we know, or at least what we think is the quality of what we know. All right, so we talked about heterogeneous and homogeneous yesterday. Heterogeneous agents generally mean that it means that you have agents that are not just copies of each other. So one of the interesting things about software is if you design an agent, you can make 1,000,000 of them for free, right? You just in your simulation say, I got 1,000,000 of these things, and then you just keep track of the data for each one. So when you do that, you literally have homogeneous agents, right? They're all literally the same. They all have the same capabilities. With heterogeneous agents, though, you have agents with different capabilities. So we can talk about generalists versus specialists. If you have let's say you have, I would love to build and I have no idea how to do this, by the way. I would love to build a kind of escape room or escape dungeon kind of simulation where people have to put together teams of agents, and then once they do, the human has absolutely no control whatsoever. They just put their team into this environment, and the team has to work out how to get through. Kind of based more on a cooperative game, more than like a D&D style game, right? So.
By teams of agents, you mean like give them personalities or give them like skills?
Skills,
okay.
Right. So give them skills, right? And then again, you can think about if you had a menu of, well, I've got a game kind of like that I'm asking the game design group to build. We'll see if they will or not. I hope they do. So here's my game, right? Here's my game. It's capture the flag, right? So literally you have to go grab the flag from some opponent's home base, and bring it to your home base, okay? It's in flat world, so there's no obstacles, and there's a couple of different kinds of agents. One kind of agent will move out and over, and if they come in contact with an agent from another team, that other agent from the other team it goes to sleep for like 3 turns. And then another agent is, if it comes in contact with an agent from another team, it reduces its strength. And eventually, if you reduce the strength to 0, that agent gets removed from the game. Another agent is basically defensive. It comes out and it sets up like a wall, and if you bump into it, you can't get around it. So these are just different kinds of agents. And the question is, can you build a team? And then once you build your team, someone else builds their team, and then you put the two teams in the arena and you say go, and the human has no more interaction. But that would be an example of a set of heterogeneous agents, because they have different movement patterns and they have different effects when they come into contact with elements of the other team. Some can carry the flag, some can't. Yes.
So kind of like chess with stats.
Chess is a perfect example. Assuming those pieces had agency, right? Then yes, they're heterogeneous.
The wizard's chess.
Pawns are homogeneous, right? Bishops within their set are homogeneous, but within the old set, heterogeneous. And the only difference again is, so this would be interesting, right? So tell me about wizard's chess. Is this
It's a joke from Harry Potter. The chess pieces don't always listen to you.
Okay.
Unless they respect you, they're not going to go run and opponent's not going to run and sacrifice.
Okay. So that would be an interesting thing to have a system where the pieces are the agents, as opposed to normally with a chess game, there's one agent called the player who is moving the pieces, right? But yeah, give the pieces some agency and see what happens. That'd be an interesting thing. But that's the idea behind heterogeneous and homogeneous. And I mentioned yesterday that Naval Research Lab did an experiment 20 years ago where they were doing machine learning experiments, and they had a simulated sheepdog, which was like a circle on a screen, and simulated sheep, which were circles on a screen. And the sheepdog was adaptive, so over time it learned how to herd and corral the sheep. Then they introduced another sheepdog, and the two sheepdogs learned to cooperate. And again, it wasn't through cooperation like explicit communication. They were just reacting to each other as parts of the environment. And those two dogs would be homogeneous agents at that time. Then they introduced the wolf, and then you have to make a decision. If you're a dog, do I continue to herd the sheep or do I chase the wolf away? And then you can start to get into, should you have homogeneous or heterogeneous dog agents? Should there be a dog agent who specializes in chasing away wolves and another one that specializes in herding sheep, or should they both be the same? So you make these decisions. So for example, Alex is doing the UAV, how do we all get along in the same airspace kind of thing. That's a decision you have to make, right? Homogeneous, heterogeneous. William, you definitely need heterogeneous because you've got the crazy motorcycle rider. And that's a pretty judgmental term, but you've got the motorcycle rider that is disrupting the traffic flow that the cars are assuming. Now, within the automobiles, though, you get to make another decision. Do you want to have homogeneous behaviors for the automobiles, or do you want to have some drivers reacting differently? And in a real traffic simulation, you probably should have a boundary of behaviors, and some of them are at the higher boundary, like they tend to go faster or be more aggressive drivers, or they tend to have a smaller following space or versus a larger following space, those kinds of things. And so you can get some heterogeneity out of them based on their preferences. Okay. So from there, we can start to really classify things. What's the degree of information? Generally, when we start to think of things, again, we think like a human. And the idea is you have local information. So you say, okay, here's the agent. It's in this area, and it has local information. In other words, it's observing whatever it can observe from that situation, from that vantage point. If you're in a simulation that has actual terrain, then that can be very important. If you are in any of these shoot 'em up games, line of sight is really important, right? You need to figure out what you can see. The agent's in a building, it won't be able to see around the building very much. So line of sight is restricted. But because it's a simulation, you can let that agent have access to all of the information in the simulation. with God's eye view. So you have to make a determination as to what is important in the sense of your experiment and what you're trying to accomplish with the simulation, and also what's feasible. Sometimes it's just easier to let that agent know everything and not have to worry about developing some kind of a process to filter what the agent is and isn't allowed to know. Now, if you remember in the Boyd's example that we looked at yesterday, in the Boyd's example, the Boyds were flocking together, and the way they did that was they were looking at their local group and then doing some calculations to get 3 vectors and then summing the vectors together to get a single vector for their movement for that moment in time, for that one time step. And on the bottom, they had different ways you could weight things or change the values of things. And on the farthest right, it was radius. And so what was that radius? Basically, it was a way to control how big of a radius an individual agent would draw. And it would basically say, okay, I'm going to pay attention to everybody within X units of me. In other words, it wasn't God's eye view. That was local information. The local information, again, you could affect through that one widget where you change the radius of what it's looking at. And as you could imagine, if you make the radius really, really small, the system won't come together very well. It won't flock very well. If you make it too large, I don't know what happens. It probably still doesn't flock very well initially because there might be some chaos. I don't know. You'd have to play with that. And then, of course, is there memory. So that's about information. Notice that's not about deliberation, which would include future planning. It's about, do you have some kind of memory? One of the things that's interesting, by the way, with agents, that's what I meant to mention a while ago, with learning agents. If you have a bunch of agents in a simulation or in the real world and they're learning and one of them learns something good, helpful, then they've all learned it. So one of the things that's kind of neat is if some agent learns a new rule that was effective, it can immediately disseminate that rule to all the other agents, assuming you've incorporated that in your simulation. Whereas, as you know, humans can't do that, right? That's why you're paying all this money to go to school, is so that we can try to help, right, develop skill levels. We can't just, the old joke, put your textbook under the pillow and wake up knowing everything in the textbook. Okay, how much intelligence? We talked about reactive, deliberative, planning, and adaptive. And again, each one of those, reactive means you just moment by moment. I'm looking at my simulation, I'm looking at my situation, making a decision right now. Deliberative, I plan ahead. I'm sorry, I have some kind of a way to either plan or look at history. Planning, I'm trying to plan ahead. Adaptive, I can change my behavior over time. So you can see right away, if you said to somebody, oh, I have a reactive agent, or versus I have a planning agent, you've given them a lot of information immediately about your simulation. Oh yeah, I've got a planning agent, but it's not adaptive. Okay. It thinks ahead, but it doesn't learn new stuff. Right? Then the degree of interaction. One is no recognition of other agents. In other words, in that sheepdog simulation, the dogs didn't really recognize the dogs as, quote, hey, there's another agent just like me. It was just, here's something in the environment. That's it. It recognized sheep because it had to go chase them. It recognized wolves, you distinguish wolves. But the other dog literally was just, there's something in the environment. Like if there was a rock there or something. So you can develop simulations with no recognition. That doesn't mean that they necessarily don't interact, although the level of interaction is pretty low. Usually the level of interaction is like, don't run into each other. But I'm not recognizing you as a similar agent. You're just something I don't want to run into. Then you can have an implied communication. Now you're having actual communication transferred between the agents, but it's not like message sending. It's just, oh, that agent is, I'm observing that agent and I can tell something about it, or I can tell something about the state of the environment that we're in by observing this agent. Generally, there's no intention to do the communication. You are just, one agent is just picking it up, even though the agent that is being observed is not intending to communicate. There's some information that can be gained. So my example, you see a car driving down the road, your car was weaving. That car is not trying to give you information, but it is giving you information of, stay back. That driver is not behaving well. Then you can have explicit communication, and I'm splitting that up into passive and active. And we've talked some about this too. The idea here is there's intentionality. There's intention to communicate. So I can have an intention to communicate, but I'm not broadcasting messages. So basically, I'm relying on you to observe me. Now, we can argue about whether like brake lights or flashers, oh gosh, is that, is that sending out information, right? Is that sending a message, or is that I need you to observe me? That's a tough one. Some agents, I've got a coffee maker, I turn it on, and the buttons have flashing lights until it gets hot enough, and then the lights are solid. That's communication, right? But it relies on me observing. So I don't know, was that a message sent, or was it, right? I think that's passive still. Whereas in the active, you are intentionally sending out information. And it could be broadcast, like I'm just sending this information out, I don't care who gets it, or it could be directed. I'm only going to give this message to you. I'm only going to give this message to you. Foghorn, sending a message, right? But it's broadcast. We don't care what ships hear this. Nobody hits the rocks, okay? These explicit communications, again, tend to be broadcast. So for example, if you have a simulation with ships, and one ship is in distress, and so it raises a flag that says I'm in distress, I would argue that that is a more passive form of communication because it's relying on others to observe the flag, as opposed to sending a radio message out, either broadcast or specifically to, okay, ground station, whatever. You see this with pilots, right? They're going to communicate with the tower. Hey, we've got an emergency situation. We need to land, blah, blah, blah. That's explicit communication. Now, if the tower sees the aircraft going by and there's smoke coming out of the engine, that's a passive form of communication. That agent it did not even intend to communicate. It just happens to be that the engine's on fire. You see examples of that sometimes. Every now and then, doesn't happen often, but every now and then, you hear about aircraft where the aircraft decompresses at high levels and it's on autopilot, so everybody inside is either passed out or dead, but the plane just keeps going until it runs out of fuel and it's going straight and level and it's ignoring all the FAA attempts to contact it. Right. Every now and then you hear about that. There was a golfer, I don't know, quite a few years ago, who passed away. That was private jet, and it just kept flying until it ran out of fuel. And wasn't there the Malaysian jet 10, 15 years ago, the one that disappeared? They can't find it. But for a long time, it was straight level flight, not responding. Right. So that agent is giving you information, right? The information is, something's wrong here. We don't know what's wrong, but something's wrong. It's not responding to us, but it's in controlled flight. But since it's straight and level, it looks like it's autopilot and not a human. Similarly with the hijackers 9/11, right? They started not responding to responses, right? Something's wrong. Yeah.
What's the difference between implied communication and then passive communication?
With passive, there's an intention still. I want to communicate, but I'm not going to broadcast a message. I'm going to I'm going to turn a light on myself. Like I'm low on battery power, so I'm going to put a yellow light on top of my head. And now it's still, I'm not sending the message out to you, right? I didn't radio home and say, hey, I'm running out of battery power. I just put this on. So anybody who observes me can say, oh, that agent is trying to tell me something. It could also be, if you have agents that are supposed to do some kind of task sharing, you've got a bunch of tasks and the agents are supposed to work together to get tasks. If I don't have a partner, I'll put on a green light, and that way, you can have a green light and we can say, okay, we'll team up and do a task. And then we'll say red light, okay, we're already teamed up. So we're intending to communicate something, but someone has to observe us in order for that to happen. Does that make sense? As opposed to, if you don't intend to communicate, if you've seen a bird that's damaged and it's flopping around on the ground, that bird is just damaged. It's not intending to communicate. But there are birds who will fake that with an intention to communicate to draw predators away from a nest. And then we can get into social rules. So the idea with social rules is that you have pre-planned ways that you behave with each other. And the idea here is to try to increase efficiency. We are, as humans, super involved with social rules. If we didn't have social rules, so much of your day would be spent negotiating with other people. And we do it so well that unless you consciously choose to be aware of it, which I invite you to do, if you consciously choose to be aware of it, you'll notice that you are engaged in constant negotiation with people, constant. And that negotiation goes really fast because we all have the same social rules. And as you know, as you go around the world, you may encounter different social rules, where the social rules actually aggravate a situation instead of making things easier. It's so simple. And my example here is the stop sign, four-way stop. I know we all know the rules. I got there first, the other car's there, they got there second. We both know I'm going first, but I tend to make sure I just make real quick eye contact. Or real quick, check that car, make sure it's not starting to move. It's that quick of a negotiation. Who's going to go? Eye contact, I go. It's that quick. You see it in the grocery store. I mean, again, it's all these mundane situations, but it exists. You get to the grocery store, you're pushing the cart down the aisle, someone else is pushing the cart down the aisle. Generally, we both go to the right, right? And if you notice, pay attention. They might move their cart just the slightest amount to the right. And what are they doing? They're opening the negotiation. They're offering, I'm going to go to this side of the aisle. Okay, I'll take the other side. If you want to really see it in action, don't accept the offer. Try to go to the same side. Right? And you'll see now there's a negotiation. And you've done that game too, right? Where you're like, you are in a kind of a crowded space and you come up against a person and you try to get around, but you both go to the same side at the same time and you do that back and forth thing for a second. Right? What are you doing? You're negotiating. If you had to spend all your time negotiating from scratch, you wouldn't get anything done. But the fact that we have all these social rules, look at the way you go through doors. by the way, on campus here, we have a crazy holding door social custom. People will hold the door open for people so far back compared to other environments. I think it's great, right? I'm 10 feet back and someone's holding the door for me. Oh, that's great.
Doors over there, heavy as heck.
Yeah. But if you go to, I don't know, go to the library or something, off campus, right? Go off campus where there's no automatic, someplace where there's no automatic doors, and people aren't that accommodated with the door holding. Now, what I don't get, and I don't know how you could ever figure it out, people don't just come here that way, right? They're picking up that social behavior in their time here. But am I wrong? I mean, doesn't it seem like people hold doors from a lot longer distance than in other places? It's a social custom.
I'm gonna be honest with you, I've noticed that it tends to be more for the people who, I'm just gonna say it, look like you and me. We look older and we continue.
Oh, maybe that's why I see it, yeah.
We tend to get the door held open for us. I have noticed, like one day I have very few pair of pants that actually fit over my knee brace and one day he was feeling sick and he didn't come with me. I noticed that on that day, I just happened to have a coincidence where I was wearing no knee brace and the distance that people would hold the door
Was
so I'm sorry, but I think it's more of an ageist.
Oh, could be me, all right.
Alright, but I do believe that as far as holding doors on this campus, people hold doors more often than they will elsewhere.
It seems that way to me. And again, maybe my experience is unique because I'm old, yeah. So it might be just a factor too of in a school situation, you have a lot of people going through hallways all the time, so holding doors becomes a thing, right? Now, again, holding doors is like a trivial thing to talk about, but it's a social rule. And you probably weren't even aware it was a social rule until we actually started talking about it. They're everywhere. They're everywhere. Yeah, I could see with you, everyone just like your dog too. So, you can, so how do you incorporate that in a simulation? Well, again, there's different ways, right? So I've talked about ants a lot, and people study bees. People study, I think how whales hunt together. People study how wolves work. So you look at different social dynamics, and then you try to incorporate those rules somehow in your simulation. It depends on what your simulation is. It might be pheromone tracking. It might be some kind of a history built up that creates a dominance hierarchy. It might be something else. It might be, let's say, an agent-based system. I saw an agent-based system a long time ago, and it was done with these little robots. They were like about the size of I don't know, about the size of a coaster, but smaller. And these little robots were in a circular flat world. And in the circular flat world, there were little dowels stuck in periodically. And when the robot encountered a dowel, its job was to pull it out and just set it down on the ground. So it would pull it out of the hole, okay? And then if it did pull it out of the hole, it would do a little happy dance. It's kind of a nice feature. Then some of the dowels, though, were too long. So one robot couldn't pull it out. It would pull it out so far and then hold it. And if another robot at that point came along and pulled it again, it would get the dowel out. So by teamwork, they would get the dowel out. But there were no social rules in this thing. This person was just studying what the heck is going on here. How do you get this spontaneous interaction, right? So these robots were reactive. They were only responding to their environment. They were not deliberative or planning or anything like that. They certainly were not communicating, and they did not even have interactions with each other. They didn't recognize each other. It was literally, if I happened to be holding a dowel and another robot stumbled by and picked up the dowel again, then we would have success as a team. I have to use the word team loosely there because it wasn't really a team. The first thing I thought of, and unfortunately I didn't work with the person who did this, so I never was able to follow up with them. But I thought it would be interesting to introduce a social rule where they liked to travel in pairs. So they would travel randomly, but they traveled randomly singly. But what if you did a simple social rule where they like to travel in pairs? Would that increase the efficiency of the overall system? I don't know. But what a simple social rule to make, right? So you can make any social rule you like in your system. The trick, as always, with software is how do I represent it in data form? How do I represent it in an algorithmic way that is actually something that the agent can act on? Do we have social rules involved in any of these experiments? You don't have explicit social rules, right? You've got behaviors, individual behaviors. Same with you're kind of both doing traffic study stuff. You guys don't have social rules.
I mean, for the ERAU one, I'm just gonna ask, are you going to use the social rules that are there for aviation, or are you going to set your own, trying to solve issues?
So I'm doing advanced air mobility. We don't really have rules yet for advanced air mobility. So I'm gonna try to come up with something for like intersections.
Well, that's what I'm asking.
Yeah, just did they?
Because pilots have those social rules.
Yeah,
It's usually whoever is lower has right of way. The reason being is the person who's higher usually can see the other aircraft better. That's because you have better visibility down usually.
yeah. The only issue is I'm assuming a fully autonomous flying environment, and I need to incorporate the actual concept of operations. So we'll see what ends up happening.
Right.
I don't really know what's gonna happen for advanced.
People have proposed different
Yeah,
sets of rules, haven't they?
yeah, kind
Yeah.
of. Right now, the like foreseeable future is kind of what you're talking about. We're not really assuming autonomous at all. So they're just using regular pilot rules. Before like autonomous operations,
Right,
really been research, like in research.
right.
People in academia and industry have all proposed different things. So kind of just have to choose something, I think.
And then what's odd to me with that, when we get into the real world operational environment, you might have all autonomous systems and they may have one set of rules that work great for them because the visibility issues for them are completely different. But now you get into mixed environment and you have to accommodate the human again, so you may have a different set of social rules.
And that would be the other thing, is that the faster you can travel, the more right of way you have. Like it's not like an official thing you're taught as a pilot, but and with your instructor, you sit there and you talk about the other aircraft you can see, and you'll eventually figure out that, hey, I'm in a 172. I'm gonna get passed by that Piper over there in like 30 seconds. So they always have the right of way. Because one, their necessary flight speed is higher than mine. I can get down to 80 knots and just be fine. Whereas then, if they get down to 80 knots, they're getting very close to their stall speed.
Mhm.
So I'm just pointing out the social norms that are associated with
Yeah.
pilots, because none of these are rules. These are not official rules. It's
Right.
behaviors you're taught to like as a child, hey, you're coming towards each other in the aisle, you go to the right, you figure it out. Where in aviation, we have that, it's usually whoever sees the other person first, because there has to be that radio communication if you're going into a congested area. Hey, I see you, you're at my forward right, I'm at your such and such. And then the other person will look back and go, I see you, you're up there, and I'll let you go over. That's one of those things of figuring out who has more energy, who needs to go faster. And I think as part of that, if you want to throw a wrench into your system, is make it where the drones are always giving a wider berth to human ones, because they won't communicate as fast.
There's a couple, yeah, and we can have a whole, no, it's okay. We can have the rest of the week on this discussion because it's a really rich discussion and you have so many options. You could, well, then we look at like, how does ADSB affect that? Because now everybody, if they're all ADSB equipped, can see each other.
Drones will be,
But-
Air Mobile might have that, but.
Oh, yeah. But yeah, drones will have different sets of visibility. Forgot what I was gonna say. Okay, so, and then heterogeneous versus homogeneous, as we discussed before. So you can describe an agent based on these four characteristics. How much information do they have? How much intelligence do they have? What degree of interaction do they have? And are they homogeneous or not? And if you're describing those things, you basically describe, you can give a lot of information to somebody with just a few words based on those categories. So your agents are nodes in a graph. Where do they fall on this? How much information do they have?
Well, it depends on what is being to them, but typically local, maybe memory.
It's local, right? Yeah, now, yeah, you're right. Depending on how much you want to play with the model, you can give them memory, but they only have local information, and the local information is the nodes that are connected to them. Like, that's all they know, is they only know their neighbors, right? Degree of intelligence. Are they reactive, deliberative, planning, adaptive? What they're doing are fuzzy cognitive maps, which are the system level representations. You're reactive, yeah. Now you can have, again, if you make it adaptive, then that's a whole nother project, right? Where you have to put a learning system on top of this. But just the basic model that you have is reactive. They're operating with whatever happened in the last time step. Even if we're saying that they behave differently at different levels of change or different levels of whatever their values are, even if you're saying they behave differently for that, it's still reactive. That's not adaptive, because they're not changing their behavior, they're not learning new behavior, right, or introducing new behavior. You've just set up a bunch of rules that say, hey, if you're low, do this. If you're in the middle, do this. If you're high, do this. But once you set those rules, there's no adaptation. Does that make sense, the distinction between them? The degree of interaction, they have explicit communication. Oh, I'm sorry, but it's not passive. It's explicit communication and it's active, right? If you have a change, you shoot that change down the edges to all of the nodes that you're connected with. And there's no social rules. Again, you can keep making, you can see how you can make a million variations on this basic model.
Can you scroll up to the other section?
With the
Yeah, for the
intelligence, okay.
What would be the difference between like the reactive and the planning? Because you could make the nodes like plan for if it gets to this or this or this, do this action.
So the difference is I receive the information at the moment. If I make my decision only based on that, without considering what the future holds, then it's reactive. If I just receive the information at the moment, and then I say, oh, based on what I see at the moment, I think I can do this in the next 3 time steps, looks like this. Now we're planning. Okay.
So it's more of the agent doing the planning versus the user planning out what the agent should do.
Exactly.
Okay.
It has nothing to do with the human who programmed it or is interacting with it. It's the agent, right? And quite frankly, the reactive agents are great because they're so easy to build. The planning agents are difficult, right? Like, I don't know, planning agent? Does a vehicle need to be a planning agent? Does it need to be thinking 3 time steps ahead or 10 time steps ahead or anything like that? I don't know.
I mean, I'm sure AVs have that ability.
I wouldn't depend on that. It depends, I guess. Now it gets down to semantics of planning. They have an internal map. They know at this light, they're gonna turn left and, whatever, right? But in terms of what they're doing at the moment, I think they're purely reactive.
I would say like Tesla, for example, has so much crowdsourced information. So like you could look at motorcycles and it's like very unpredictable because everyone rides differently.
Right.
But just like chess, where there's only so many moves, which like you said, could be exponential into like crazy components. But essentially, like you could look at a motorcycle like, okay, they're either gonna speed up, slow down, or cut over. And I think that with crowdsourced and machine learning, like that they're probably getting to understand all the possibilities that that motorcycle could maybe do. Does that make sense?
Yeah, but then
That's not really 3 steps ahead.
but then, you're listing the options, but in terms of the decision that's being made at any point in time,
It's still reactive.
it's still reactive, I think. Yeah. Yeah, because I don't think like a self-driving car, it is reacting at the moment. I don't think it's like, oh, I'm gonna go this speed now so that I can lane change in the future, that kind of thing. That'd be interesting to see. Let's say, think about how you get around a slow driver. Is that reactive or planning, right? It's like, okay, I need to get around this person, but I need to wait for this other person to pass me so the lane will be clear. Is that reactive or planning? It sounds like planning. I don't think they do that. I'm thinking about as a human, you tend to do that. You tend to have an intention that's going to happen in the future, which is kind of the heart of planning. Okay. Think of other areas. Now, there would be one. I've played board games, prior to computers, playing board games where like to try to model air warfare with a board game, really difficult. One of the things they would do is you have to write your moves like 3 moves ahead, right? So whatever your airplane in the game is doing was actually decided 3 turns ago. And the reason was it's kind of trying to simulate reaction time, right? And just the mass of an aircraft that can't magically turn on them. So is that a planning agent or is that a reactive agent? I think it's still reactive. You're reacting in the moment. The effects won't show up in the game until 3 turns up, 3 time steps up. So from that aspect, I would call it reactive, but it's created a plan, but that plan was never, you never laid out like 3 or 4 or 5 steps all at one time, like a true plan. Yeah.
So then is it like planning can be reactive?
I'm saying
The other
that
way around?
I'm saying that the decision making was reactive, but the system required that there be a time lag between the decision and the action. So it's still a reactive decision. It just took time for the action to come out. And we mentioned that actually with your fuzzy cognitive maps, if you put a delay in there, I would say that's not planning. It's still a reactive effect, but it's still it's just a time lag between when the effect takes place.
Well, then for like the chess example, you could say it's all reactive, or you could say it's planning, because you're planning out the steps ahead to figure out the best move, but you're also reacting to the other person.
Okay, so here's the distinction. For the airplane game, I am not planning my steps ahead of time. I'm reacting in the moment, which creates a 3-step or 5-step path. Whereas with the chess game, I am actively looking 3 and 5 steps ahead. I see what you're saying, because you didn't create a plan, you still made just one move, even though you looked 5 steps ahead.
Yes.
Yeah. However, I guess that could be modified where you assume blue sky, things were gonna go this way, and that would be your plan, which then would be modified if a different move was made. Yeah, I see what you're saying, but there is a sense of planning ahead in that the computer, before it makes a decision about one move, it does look 2, 3, 5 steps ahead, moves ahead. Whereas with the airplane example, you made that decision for that move without explicitly planning ahead. You're just reacting in the moment. Now, again, there was a time delay before that move became a reality on the board.
So it's based more on the context of why you're doing the move?
It's based on what you're taking into account when the decision is made. Because remember, agents are decision makers. So what are you taking into account when the decision is made? And if you're taking into account the anticipation of future events, we could call that planning. Where you've gamed out, right, or done some sandbox type stuff of here's what might happen in the future. That's more of planning. Now, actually, true, full, honest to gosh planning would be not only did you game that out, but you actually said, here's what I'm going to do now. Here's what I'm going to do next. Here's what I'm going to do next, where you make a bunch of decisions for the future and actually encode them in some kind of a data structure. That's true planning as we understand planning as humans, right? But you can also do planning where you're saying, I'm planning that this stuff will happen, but I'm only going to make this one decision now. I'll make the next decision in the next time step. But I would still call that a planning exercise in the sense that you are anticipating future events and trying to plan now in such a way to either take the most advantage or get the least risk from. Think it through and argue, right? These definitions, if we come up with good distinctions between definitions, that's called progress, right? That's a good thing. Okay, that's these notes for today. I don't know that I want to go into the next section is about experiment design. I don't know that I want to go into that. I'm okay most class days rather than having you guys listen to me the whole time, which is a hard thing to ask. I would like to spend some time in the classroom for people to discuss what's going on with their projects. So right now we're getting the need for background stuff. I'm going to shut the recording off unless there's questions about the topics here.